Hi everyone, my name is Irina Mirnova, and I'm here with Dr. Antonia Humanidou to tell you about the Hands-on Science program at the University of Texas at Austin. Hands-on Science is a 4-course science content sequence for elementary education majors at UT. Our program was initiated in 2009, and it's a teacher preparation program for pre-service elementary teachers building on the nationally acclaimed UTeach program. We service about 300 students every semester, and our program features 4 interdisciplinary content courses covering physics, chemistry and geology, biology, and astronomy and earth climate. This is our team. It's led by Dr. Michael Martyr, the director of UTeach, and we have 1 faculty member for each of the 4 content areas that we teach. I'm the astronomer, Dr. Humanidou is in physics, and then we have a biologist and a geologist as well. Our method is based on Physics and Everyday Thinking by Goldberg, Robinson, and Otero. We've expanded their physics curriculum to the other 4 areas in our science sequence, and we teach our courses with an inquiry-based collaborative learning model, and we have learning assistants that support our students. We teach via hands-on student-centered learning. Our students collect data during class in order to construct mental models of the scientific concepts. In other words, our students are learning using the same strategies which they'll be expected to use when they're teaching science in K through 5. The main motivation for hands-on science were some pressing issues that were identified in 1996 by the National Commission for Teaching. And these issues were relevant to what elementary education majors dealt with at UT prior to the development of our program. So before hands-on science, they had to fulfill their science content requirement by taking large introductory classes in physics, chemistry, bio, or astronomy. So they were learning their science content in a really disjointed manner without the opportunity to see connections between the material. And in addition, these large intro classes, they cover a lot of content, but none of it very deeply. And they're taught in these huge lecture halls with hundreds of students. They're super impersonal, and collaboration is really hard between students. Research has shown that this doesn't allow for a deep understanding or retention of the material. In contrast, elementary school teachers are expected to know all the sciences and teach them using best practices when they go through K through 5. Finally, these lecture classes that they used to have to take have a lot of scientific jargon, which is super confusing and hinders their understanding. Elementary school teachers have a huge impact on their students' trajectory in academics. And based on their elementary science experience, students are going to make decisions which are going to affect what classes they'll be prepared to take in college. So it's disturbing that elementary ed majors entering into college, they have very negative attitudes towards science. They have low confidence in learning and teaching science. They think science is hard and frustrating and scary, and they don't see the relevance between what they're learning in science and their everyday lives. So we want to change these attitudes to have passionate teachers that can inspire passion in their students. Our students come from the top 6% of their high school class. So they're elementary ed majors, and the reason they are is because they love school and they love kids. They're very organized and eager to learn. However, they do lack certain core concept knowledge and scientific reasoning skills that we want them to have. So I just want to show you a few examples of some common misconceptions that our students have and before they go through our program. So these are misconceptions that are held by the general student population too, and maybe even some faculty, but they're super relevant here because these are all concepts that are tested in the Texas standardized test. So they're part of the education standards that our students will be expected to teach. So an example from physics that's illustrated in the Annenberg Foundation Private Universe video has to do with circuits. So our students struggle to explain why the battery, wires, and light bulb in a circuit get hot. In addition, if they're given a battery, a wire, and a light bulb, they also can't figure out how to make the light bulb light. And like it's shown in Private Universe, even engineering students from MIT struggle with this concept. Now in astronomy, one of the education standards is understanding the phases of the moon. If you ask kids, they say the phases of the moon are caused by the Earth's shadow. College students, they say say the same thing, and some faculty also think that. Another common misconception, this time from biology, is where does the mass of the tree come from? So how does it get from a small seedling become a giant tree? So most students and even some faculty will say that the mass of the tree comes from the water or the soil or the sun, but very few will give the correct answer, which is that it comes from the carbon in the air. So what do we do differently? Here's a picture of a normal class. The students are working in groups, and the two guys that are standing up are the LAs. As I mentioned previously, we want to teach the students relevant topics that they'll be expected to teach. So how do we do that? We start with the Science Generalist Educator Certification Standards, and we build our curriculum around those standards. So this figure here shows an example from our physics class where we list each standard and how it's covered in each one of our course activities. And we did this for all 4 of our classes: physics, chem, geo, biology, and astronomy. In order for the students to see the connections between the different fields of science, our curriculum is based around 2 big ideas that act as a common thread throughout the sequence. The first is the flow of energy between systems, and the second is the small particle nature of matter. Here's an overview of how these concepts show up in each of the 4 classes. So for example, the concept of energy transfer shows up when we study electrical circuits in physics, photosynthesis in bio, plate tectonics in geology, and finally earth climate in astronomy. How is a typical class structured? So first we set up our classroom differently than a large lecture hall. The students sit around tables in groups of 4, and we have projectors around the classroom for sharing out. And the image up at the top shows a panoramic view of the students, where some students are presenting and others are listening. So again, we based our lesson structure on physics and everyday thinking, expanding their model to all 4 areas of science. Every lesson starts with a purpose, key questions of the day, and then we do initial ideas, we collect data, and finally we do summarizing questions. This is a closer look at the purpose section, which provides context to the students about the concept of the day and sets up the big questions we'll be trying to answer. Next, we do initial ideas, where we brainstorm what we already know about these science concepts. Research shows that students are not a blank slate to fill with knowledge, so in order to teach them something new, we have to acknowledge what they already know and build on it. Students will brainstorm in groups and share out their ideas. We don't tell them which ideas are right or wrong, so that piques their curiosity to find out. And finally, the instructor gets to see what misconceptions the students are coming in with. Next, the bulk of class time is spent on doing hands-on activities, collecting evidence. The course packet questions guide the students in interpreting their evidence and formulating ideas, with the instructor and the LAs helping. And in this picture, the students, you can see they're working through one of the astronomy lessons on optics, learning about refraction. Finally, the students answer a set of summarizing questions meant to help them synthesize the big ideas. The summarizing questions also refer back to the initial ideas questions, and sometimes the students will see a discrepancy between what they initially thought and what they found is true based on evidence, and this helps them restructure their mental model. As the students are answering summarizing questions, we also have them present their answer to the class, and then we have a discussion. This allows the students to build confidence in talking about science and to hone their teaching skills. You may be wondering, how the heck did we teach our courses this semester 100% virtually? So we tried to maintain as much as possible of the investigative spirit and structure of our classes. Our classes were all synchronous on Zoom, with the students still collaborating in breakout rooms. Instead of doing hands-on experiments, we recorded videos of all of our experiments, and the students would watch them and interpret them together in their groups, aided by the LAs. And when we discussed summarizing questions and initial ideas, we did that using Jamboards and Google Slides, so the students could still share and practice talking about science. And I think it's important to note that we had close to 100% attendance in our live Zoom meetings every class period. And of course, we recorded the classes to have an asynchronous option for students who couldn't attend live. So I'm going to turn it around now to Dr. Humanidu, who is going to talk about the assessment of the program.
Okay, so like Dr. Marinova described, the hands-on science program was designed with two main goals in mind: to teach appropriate science content to pre-service elementary students at UT, and to teach it well such that students feel confident in their ability to teach it themselves. So the question we wanted to study was whether students enrolled in the hands-on science program benefit more from our courses than they would have had they enrolled in general lecture-based introductory science courses. Specifically, we wanted to study how changes in content knowledge and students' attitudes compare between the two groups. And to answer these questions, we did a multi-semester study to examine how exposure of pre-service elementary teachers to our inquiry-based, learner-centered science content courses affects their conceptual understanding of science content knowledge and their attitudes towards science. We collected data from two groups, one composed of students enrolled in the hands-on science courses, which is the treatment group, and a control group composed of non-science, non-education students enrolled in the traditional intro-science courses through the College of Natural Sciences. And results of this study show that our hands-on science students outperform their counterparts in traditional courses in terms of relevant content knowledge gains and leave the program with improved attitudes towards science. As part of this study, we administered pre and post assessments from the Mozart group, which stands for Misconceptions-Oriented, Standards-Based Assessment Resources for Teachers. The Mozart items are based on the National Science Education Standards and are field-tested questions of varying difficulty levels with attractive research-based distractors, which allow us to probe for student misconceptions. These tests were administered during the first and last week of the semester in class. We collected data for content areas in the 5 areas of physics, chemistry, geology, biology, and astronomy. The treatment group was composed of 879 students in the 4 hands-on science courses, and the control group was made up of 503 students in the traditional intro courses. Our analysis only includes students with a paired pre and post score, and the graph here shows the means of pre and post tests for both groups. The arrows show point from pre to post test average for each group. The blue arrows represent the hands-on science students, and the red arrows correspond to the control students. And what we see is that in all categories, the hands-on science students show significant increases in their content knowledge after taking 1 semester of a hands-on science course. And in contrast, the control group shows smaller or no gains during the same time interval. In fact, 3 out of the 5 content areas tested show a decrease in the test average after taking a traditional science course, suggesting that students are actually more likely to answer incorrectly after taking that course. The only content area in which the control group students showed a gain was astronomy, but that gain is much smaller than that seen for the hands-on science students. It's also interesting to note that both for physics and astronomy, even though our students start with a lower pre-test average than the control group, they reach a post-test average higher than the control group's pre-test average. A note on the geology, you may have noticed that we don't have data for the control group in this case. This is because we couldn't find an appropriate control group for this particular content area, but it's still worthwhile to note that our students still show a significant gain from pre to post average score. In addition to looking at the pre and post test means for each content area, we also calculated the normalized gain for the two groups. So the normalized gain represents the change in student score as a fraction of the total possible improvement on that assessment. So for example, if a student scores 50 out of 100 possible points on a pre-test, they have room to improve by 50 points. So if they then score 75 out of 100 in the post-test, they have a normalized gain of 0.5, meaning that they increase the score by half of the possible amount. So the table here presents the pre and post test average that I talked about earlier, as well as the normalized gain for each of the two groups and each of the 5 content areas tested. So what we see here is that the hands-on science students improve in all 5 content areas assessed by as much as 0.39 normalized gains. And in contrast, the control group shows negative normalized gains for 3 of the 5 content areas assessed, suggesting again that they're more likely to answer incorrectly at the end of the intro science course that they took. So in addition to studying conceptual gains for students in our classes, we also investigated our students' shifts in attitude towards science in general and learning science in particular. We administered a 21-item Likert scale survey adapted from pre-existing surveys such as the Math Anxiety Rating Scale and other items developed by the National Center for Education Statistics. The surveys again were done online and administered during class. The two groups were composed of 238 hands-on science students and 263 students in the intro science courses. While our survey represents many different ideas students have about learning science, we classified the questions in 4 different categories. Students' confidence in their ability to do science, their enjoyment towards science, how anxious science makes them, and how relevant they feel that science is to their lives. And we asked the students to rank how each situation applies to them. Note that some questions, such as those for anxiety, are worded negatively, such that a high score corresponds to high anxiety. So what we see once again, when we compare the means of the pre and post test for the 4 categories, is that there was a change in attitude occurred for both groups and in all categories, but in opposite directions. The solid lines here represents the hands-on science students, and the dashed lines represent the control group students. And the results of paired t-tests indicate a statistical significant improvement over time for each category for the hands-on science students. And in contrast, patterns for those in the comparison group reveal a decline in favorable attitudes towards science. Interestingly, the largest change for the hands-on science students was observed for the anxiety category. We note that the two groups don't differ significantly on the pre-survey, but the hands-on science students report a significant decrease in how anxious science makes them after taking our courses, while the control group students show a slight increase in anxiety after taking the intro science course. And similarly for confidence, while hands-on science students initially had lower science confidence than their non-hands-on science peers, they significantly increased their confidence over time, while the opposite thing happened for non-hands-on science students. The enjoyment and relevance categories show similar patterns as you can see from the graphs. So our data analysis shows a remarkably consistent and positive story for the hands-on science students. Our students significantly changed their views towards science from the pre to the post survey, such that after participating in the hands-on science program, they report more confidence in their skills as science learners, more enjoyment and less anxiety towards science, and perceive science as more relevant to their lives. So they go from saying things such as, I'm not good at science, to I did well in my science class, or science is hard and frustrating, to science is fun, or science is scary, gets replaced by I can do science. And finally, science doesn't apply to my life, to what I learned in my science class shows up in my life. So getting students to understand the nature of science is definitely a worthwhile goal, especially for future teachers.
So just going back to some of the issues that I introduced earlier, our sequence, our program solves these issues because we integrate our 4-course science sequence with common ideas. We map our classes to the educator standards so they're relevant. Our students learn by doing. They focus on collaboration, asking questions and discussion, and we strip out jargon and just use the most fundamental terms.
So to summarize, the Hands-on Science program is a 4-semester sequence of science content courses taught using the same hands-on model that teachers must follow. It's an integral part of pre-service teacher professional development. It integrates many disciplines to emphasize the interconnectedness between the different fields of science, and students exit with more knowledge and better understanding of content, as well as improved attitudes toward science. So it seems that we are fulfilling our goals. Thank you for listening to our talk. If you have any questions, you can contact us here. And here's a list of references for those of you interested.